Hi, everyone. My name is Johannes Doerfert, and I'm here as your moderator for the first ML and LLVM panel that we have organized. So this is a live panel with 6 different panelists that will answer your questions that you hopefully have, because as you can imagine, a panel kind of lives from the questions from the audience. But such to get you to introduce the panelists, which have various different backgrounds and different experiences, they prepared a short introduction, like a few slides, a short introduction into where they're coming from, how they interact with ML and LLVM. And we'll start with that. And our first panelist that does so is Alok. I'm very happy that he's here. And Alok, the stage is yours.
Thanks, Johannes, for the introduction. So, hello, everyone. My name is Alok Mishra, and I am doing my PhD in computer science under the advisory of Dr. Barbara Chapman. Now, there are numerous use cases of how machine learning can help compiler optimization. Today, I'll be talking about one such optimization that we are working on. Now, this is a work done under the ECP project in collaboration of Stony Brook University and Brookhaven National Laboratory. CompOff is a tool that utilizes machine learning to predict the cost of offloading a piece of OpenMP code to the GPU. It can be used as a standalone tool or a cost model during compile time to determine whether offloading a kernel to the GPU will be beneficial or not. So before we move on, I just wanted to let you know what to expect from this tool. So this is a tool which can be used by both compiler developers and application scientists, and it helps predict the cost of offloading a piece of OpenMP code to the GPU. The unit of prediction is in seconds. The main goal behind this tool is to maintain portability of OpenMP, such that it doesn't just predict the cost of OpenMP code when built with LLVM, but also other compilers like GCC, Intel, etc., and on multiple HPC clusters like Summit or Ukami or Stony Brook University's own HPC cluster, Seaworld. Now, as such, to maintain the portability, as of yet, we are doing all our analysis and feature extraction on the AST itself and not going down the level in compiler. Having said that, if we want to use this tool as an LLVM extension, we can use LLVM IR, which will undoubtedly improve the tool's performance. Right now, the tool is generic, and this is still an early work, and there are room for improvement. So what are the hurdles that one faces when dealing with GPU offloading? You see, it is quite challenging to optimize large-scale applications consisting tens to hundreds and thousands of lines of code. We must first ask ourselves, what are the programming complexity of the code? Or is it portable to the GPUs available? Is the code parallel enough to justify GPU execution? How is the data being handled in the code? To minimize these challenges, we can use something like OpenMP, which now supports GPU offloading as well. However, effectively pragmatizing each kernel is a repetitive and complex task. To solve this problem, we developed a compiler framework to automatically transform an OpenMP parallel loop to support GPU offloading. How do we do it? Our framework takes as input a C code, identifies OpenMP parallel loop, suggests several kernel variants which can be used to offload to the GPU, and using CompOff, which is a neural network-based cost model, it predicts the cost of execution of each of these variants to select the best amongst them. Now, I will not get into the details of my framework today, but if anyone's interested, I would love to talk to them after this session is over. So let me just jump to some of the results of our cost model. We divided our data set into 70% training and 30% testing data set. And then we trained our model using a deep residual regression model. And when we predicted on our testing data set, we do see some patterns here. The blue dots here are our predictions, while the yellow line is supposed to be the ideal result. We have the root mean square error for the current model as 23 seconds, which is not bad for GPU kernels, which runs for over 100 seconds. Now, we are still fine-tuning the model to make it better for future results. To test, we also wrote a program for large matrix multiplication, and we used different transformations like target teams distribute, parallel for on the main loop, or splitting the outer loop into teams and the inner loop into threads, or collapsing the loops, etc. And we ran all these codes on different clusters. It's worth noting that these kernels of matrix multiplication were not used during training the model. and hence remain unseen by a model. The blue bar on the screen represents the actual runtime of the kernel, while the orange bar represents the prediction by CompOff. You can see that the prediction by CompOff is quite close to the actual runtime. Now, to summarize, we are working on a tool that statically estimates the cost of OpenMP offloading using neural networks. This tool is independent of compiler and hardware, although this tool is developed upon LLVM and can easily be extended to be used as an LLVM optimization. Now, I would just like to hand over the session to the next speaker. Thank you very much. If you have any questions, I will be happy to answer them.
Hi, everyone. My name is Konstantin Sidorov. I'm a master's student with Moscow Institute of Physics and Technology, and today I'm going to give a short talk about my work with LLVM related to code generation for OpenMP code generation for GPU kernels. But first of all, to explain the project, I have to give a short overview of related GPU concepts. You see, GPU, unlike CPU, is not targeted for running a few threads fast. Rather, it's targeted to run a lot of threads, and thus it's more suited for massively parallel parts of code. Well, it's hard to write general purpose code directly for GPU. There are certain frameworks that aid this kind of applications. One of them is NVIDIA CUDA, and for the purpose of this talk, we'll only need a single concept, which is thread hierarchy. Basically, in NVIDIA CUDA, threads are grouped into several layers of hierarchy, which are skimmed on slide. The example of how the CUDA kernel may look like in actual code is depicted on the slide, and as you can see, it's basically split in two parts. In one part, you define the kernel, the code that is actually run on the GPU, and the other part is the kernel invocation, in which you take a kernel and instruct the code to execute on GPU. Note that in the invocation part, you actually have to select the amount of, for example, threads per block and blocks per grid, which the numeric parameters which directly define how the code will be executed, and by extension how fast will it be executed. NVIDIA CUDA obviously is nowadays not the only framework that's used for GPU. Another one is OpenMP Offloading, which basically introduces GPU programming concept into OpenMP programming model. In the simplest case, you can basically replace the primers for normal parallel code for like GPU parallel code. And the interesting thing here is that the programmer may omit the grid dimension. He may just not mention it and let the compiler figure it out. And here's the key point of the project is that the actual choice of the grid parameters may make or break the execution of the kernel and its speed of execution. So in the scope of this project, we propose the approach that's outlined on the slide, in which we take the kernel code, translate it to the IR, and by using some heuristics, we deduce the grid parameters that are the greatest fit for running this kernel. Obviously, you can define heuristics in many different ways, but the approach that we pursued here is centered around using ML models defined on features from IR and assembly. The current status is as follows. We have the working pipeline for generating data from OpenMP kernels, and currently we're working on ML models, making decisions on what grid parameters to choose to maximize the kernel performance. The next steps that we see in this project is, first of all, integrating the model into the upstream LLVM code base, and another interesting direction is adding support for raw CUDA kernels. I guess that's it from my side. If you have any questions, feel free to ask them in Q&A. And I guess Mircea and Yundi, the floor is yours.
Hey, hi, I'm Mircea, and together with my colleague Yundi, we'll be talking about what we're doing with ML for LLVM at Google. So some of this, I mean, this is just an overview, and I mean, some of these, like the high-level principles and goals are the same as what we talked about last year at the roundtable, have been doing since. But our main goal is shipping, like, you know, like whatever we're doing, we want to contribute, and we are contributing back to LLVM, and then like using it in real life. The main focus that we're having, like, it's not like to the exclusion of everything else, but I mean, the main current focus is replacing heuristics in passes that are driven by them. So like inlining or register allocation, right? And we think that, I mean, if you look at how we do stuff without ML in these passes, we tend to improve these passes by looking at more program properties, right? And we incorporate those, and then the problem is, well, how do you combine them with what you had before to get a better optimization? So we think ML can help there, you know, like basically program properties are features. So ML does well with more and more features. And then ML automatically self-tunes. I mean, that's part of it, where like you don't have to like try it by hand. So one effect of this we hope to get is passes will get simpler because it's simpler in comparison to writing a heuristic. It's simpler to extract features and then throw them over to this, well, granted, black box that does decision making. But of course, like, you know, like one effect of that would be, yes, you know, like maybe the extraction code is simpler, but then how do you actually diagnose these policies? And that is very much acknowledged, like as part of the challenge of adopting ML in a production compiler. So from the compiler side, our main goal is to not affect the end consumer in any, like the end compiler user in any visible way. So things are the same, but just better. The compiler is deterministic, you know, like completes in a timely fashion. There's no new dependencies at runtime, you know, like at build time. It's just to get better policies, right? So that's the reason for which we're chasing for solutions, like for policies, for training algorithms that give us pretty general policies, right? Because we don't want to keep retraining them or changing them, because then it would not be transparent. For performance, we adopted the strategy of using synthetic rewards, meaning like rewards that we calculate ourselves in the compiler for training. The reason being that if we were to use benchmarks for training, benchmarks take forever to compile and run, are noisy, have second-order effects, so they're kind of like confusing to a training algorithm. In contrast, and there are not that many benchmarks, frankly. Like, I mean, compared to what we can do with synthetic rewards, where we can scale to like enormous corpora, we can have like hundreds of millions of functions, for example, for register allocation for training, and that is less noisy. Now, of course, for validation, we do run benchmarks. Yundi, you want to talk about the ML side?
Yeah, so thank you, Mircea. I'm going to talk about some details about how we get the trained policy. So we use the reinforcement learning to train the policy, which learns from the try and error. So during the training, we keep compiling the current policy to get the trained data. Then we use the data to improve the policy. This iteration between the policy training and the data collection happens repeatedly, and the policy can get better and better during this process. and after some time of training, we get a policy we are happy with, and we can directly deploy the trained policy to production. Next slide. So currently we have 3 efforts going on. Our first effort is about the inlining under OZ to reduce the binary size. We upstreamed it to LLVM the last September. Recently, our summer intern Jacob improved it by adding more features and training on larger corpuses, and we get some better model out of it. On the deployment side, we deployed it to future tool chain, so you can build a future with our machine learning policy now. Our current main focus is on the register allocation on the O3 for performance. It's upon the profile optimization and sync LTO. We have observed measurable effects in the data center workload at Google, and we are about to upstream it to LLVM. The IFC is out and Mircea is working on upstreaming the code. Our third effort is going to look back about inlining, but with O3 for performance optimization this time. It's still at a very early stage. We have all our training infrastructure on GitHub, and we welcome the contributions and collaborations from the LLVM community. So the next.
Hello, I'm Ondrej. I'm a software engineer at Google's compiler research team, and I'll be presenting work on cost models I've been doing with my colleagues Amir and Mangpo. So when we speak about cost models for machine code, what do we understand as machine code? Well, we're looking at pretty much anything that's assembly-like. So this could be x86 assembly, ARM assembly, or any other assembly you know. But it could be also another language which looks like assembly, for example, LLVM IR. And so we're looking for cost models or performance models. So why do we want them? Well, we want to use them as cost function in compiler optimizations, because all compiler optimizations do use a cost function. Some of them are implicit. We prefer to make them explicit. We could also use the cost models for analyzing existing code. And so why do we care about cost models? Well, they are much easier to compute than benchmarks. They take shorter time to compute, and they are always available. No one needs to write a benchmark. No one needs to prepare an input data set. And so what options do people usually have? Well, there are analytical models. They are easy to understand. They give explanations, but they are insanely difficult to develop and to make precise. And so we're looking for at machine learning to as a way out and as a way to scale development of cost models or performance models. And as it turns out, it's easier to get good precision than for analytical models. On the other hand, well, we have limited explanatory power from machine learning. Usually what we get is one number, and that's all. But sometimes that's good enough. So as for our current models, we're using a graph representation of code where we can capture both the data flow and some bits of control flow. And we're using this together with graph neural networks, which we have found to give us best performance. So we're with the current best model, we're getting mean average percentage error on the main Intel microarchitectures of something like 6.5%, which we believe could be improved, but at the same time, we're quite happy with what we're getting. And so to sum up, we're building cost models of machine code or any assembly-like code. And with machine learning, we can get precisions that are, or predictions that are very close to the actual runtimes. We could improve them. And what's our current state? Well, we have built all of this as experimental code, which is partially based on LLVM, but we've been building it privately. So our models work nicely on our corpus, but there is some extra work to make this 100% production ready. For example, make it generalize from one microarchitecture to another, or prepare a smooth transition to new microarchitectures when they are introduced by chip vendors. And we're considering open sourcing the code and making it available to the community. And the main thing is we're looking for applications. So if you have any ideas of how such a cost model could help in your projects, talk to me and let me know. We'll find a way to make it work. With that, thank you for listening. I'm looking forward to the discussion, and I'll hand the mic to Tarindu.
Hi everyone, I'm Tarindu. I'm an undergrad at the University of Monitor, and I will talk to you guys about our GSOC project this year, machine learning and ordering of compile optimization passes. So let's first look at the problem we are trying to solve, the optimization selection problem. So LLVM applies a sequence of passes to optimize the input code, but like selecting the ideal set of passes to optimize a given input code is not trivial, because this is due to a number of reasons. The first one is like LLVM ships with a very large number of optimization passes that you can choose from, and new passes are added every now and then. So it's really hard to select passes from this large pool. And second, the ability of a pass to actually optimize the code depends on a number of factors, such as the nature of the input code, the dependencies between passes, as well as the target hardware. And how we do this now is to use predefined pass sequences like O1, O2, and O3. So this is because like developers can't go and manually select passes every time they're trying to compile something. So they just use predefined pass pipelines. But the problem with this approach is that this is not tailored to the application being optimized. So it's designed to perform reasonably well for any generic input program. So this is not ideal, because it can result in like suboptimal performance or resource and time wastage. So it could be not pipeline passes that are needed to optimize your code, resulting in lower performance, or it could be applying passes that are not needed, wasting your resources. So for now, we mostly focus on the latter, where we want to avoid applying unnecessary passes and save compile time. But we can definitely extend the same approach to optimize the performance as well. So in our approach, we try to predict a custom pass pipeline for each LLVM function that is best suited to optimize that function. So we basically plug in a predictor into the pass manager that can select custom optimization sequences for each function. And so the prediction model we use looks like this. So we basically use a neural network, and the inputs to the model are core features that we extract from functions. These are core features like the basic block count in the function and different types of instructions and loop depths and loop counts. And then the model makes a prediction. The model makes a prediction of like which pipeline to select. So we just use like O1, O2, and O3 as a possible pipelines for now. But ideally, we should have like few custom pass pipelines we came up with for these different functions. So which will actually increase performance as well in addition to compile time. So, but this works for now to test if our approach actually works. So the idea is something like this. If the user asks for the optimization level for a program, we can switch to a lower optimization like O1 and O2 for some of the functions in that program that don't need all the optimization levels in optimizations in O3, and then we can save like compile time. During this year's GSOC, we made a lot of changes to the LLVM pass manager and pass builder to be able to do this pass pipeline switch, as well as plug in the predictor. And we also extracted a data set which has a shape as shown here. So each data point is a function, and it has like different function features, as well as a label with assigned optimization level. So, and we got these labels by simply analyzing assembly files after applying each optimization level to the function. So I could not fully complete everything during the GSOC period. So I'm currently working on training the ML model And we should be able to plug it in soon and see some more interesting results. And yeah, thank you.
Okay, we're back. So now after we heard all our panelists give a quick introduction about what they are working on in ML in LLVM, we're now at the point where people can ask questions, and you should use the Pigeonhole webpage to ask questions and vote for questions that we're going to ask our panelists now, and hopefully get some good answers out of them. So the first one to ask is, what resources are available for people interested in ML for LLVM?
You can answer that, no?
I'm here to ask questions.
Okay.
So you're up.
I can take a stab at this. And so I interpret the question in like, and let me know through Johannes if that's what you meant. There's two parts there. Like one is what's there in LLVM that you can use or reuse, and then the second one is what resources, as in like compute, are available. So let's start with the latter. So Johannes drove this. That's why I said he can answer this, because he drove this effort over the May of this year together with Tanya and Anton, yeah, where we finally managed to get the Google Cloud credits. So very long story short, there's a way you can sequester Google Cloud resources like virtual machines and do whatever you please. So like for training, presumably, like that would be probably why you need it. Now, in terms of what's there, so then like that depends on what you do. So in LLVM, we checked in infrastructure for for the work that Yundi and I are doing, like for that line of thinking, if you will, right? Like primarily what you have is like two things. One is if you need to load a TensorFlow model and interpret it, like there's a slow mode, right? Like, but it's very good for experimentation. Then we have everything you need. Like you basically like have this thing that you can load a model with, and it offers you an interface. You can modify tensors for the input and run it and all of that. The design is like, I'm very conservative with like adding APIs. Like I don't like adding APIs in general. So it's designed for what we needed. But if you need to do it, if you needed to do more, like please contribute by all means, right? So there's no, if it's not there, it's because of what I just said, not because it shouldn't be, right? So the other thing that we have is this thing that if you have a model that is pre-trained, there's a build rule that lets you AOT it, like ahead of time compile it, and you get like a pre-compiled object, and you can link it, and well, the model is fixed, but it executes very fast. So we also have that, and we have build bots. So if you want to do something with LLVM within this infrastructure, like that I just described, you don't need to ramp up build bots or anything. We have them, and they just work for anything that that uses our build flags, so which are generic. They just say like, hey, I have AOT or I have this like slow mode, and so that's what we have there right now, and it's all again like it's all open for contribution. Like if it's not there, please add it.
Sounds good.
Yeah.
I would like to add to it. I think apart from what are the resources that are available in LLVM, one more thing that is missing in machine learning is the data for compilers. And I really believe we should start some effort from our side that where we start building upon the data. Now, I agree that just like we have different optimizations, we cannot have a silver bullet for data which will cover all the optimizations. But we can at least start with some kind of a data bank, or where everyone who is working on different kind of optimization can publicly put the data. I'm just talking about the compiler side, the LLVM side. So that will be really helpful if we can. Like right now, I'm working on some data set, and pretty soon I will be making it public. So,
oh, cool. That's actually like on that. I was gonna mention, but I forgot. We have like like Google ML-compiler-opt GitHub, where we have the training infrastructure that we are using, well, in so much so there's parts of it that are specific to internals at Google, not secret internals, but just like distributed computing at Google that we couldn't open source because they make no sense. But the core of it is there. So whatever those things distributed compute is open source. And also like scripts and tools for IR extraction that are available in LLVM. Like there's a way to extract IR. So, but building on what Alok said, like, yeah, perhaps we could. I mean, Clang itself is a reasonably sized, project, and we have instructions on the aforementioned GitHub site on how to extract Fuchsia's corpus, which is also reasonable sized. But maybe we could maybe like just pre-bake it, right? It's worth at least trying. I have some reservations just from the fact that I know that we keep adding flags to the compiler, and soon enough you end up with a compiler that cannot compile the bitcode that it happens. So I'm just saying, like, so it can happen, but we could try it and see what breaks. Right?
Yeah.
Sounds good. Anyone else wants to like answer or like extend on that question? Do people use the resources that were just kind of listed here? Have any of you did that? Like used any of this?
Nope.
No.
Well, we are using
The Google folks haven't. What about the?
We are using our own.
Right. So. Okay, let's go to the next question. How are the features extracted from the IR for the deep learning models?
Manually, like meaning like we wrote code that just like you would for a heuristic. We know that it can be done better, but we started with what's easiest to do and more controllable.
So that is part of LLVM already, right?
Yeah.
Do you happen to know like how many features we currently can extract? What the status there is?
I think that it depends on the pass. So for example, for inlining, we extract like I forget after Jacob's work like 20 or 30 features. But for register allocation, they're like totally different. Like I mean, the feature set is specific to the problem, right? So we are extracting. I mean, they are like Yundi was saying, like we're pushing the code, so it should make its way there like in the next week or so. But it's I think 20 features per live range times 33 live ranges, so it's a slightly bigger packet. Because this 33, because on Intel you have 32 registers plus the candidate, and we learned, so it's not a magic number; it's a very specific number. Right. I don't know, but Tarindu, like you have your own feature set, right? Like,
yeah, I have like around the same number of features, like for the optimization selection problem we are working on. So it's like the same, around 20 to 30 features. Yeah.
But they're different. Like, I mean, even the time they are collected, you collect them at a different point in time, right?
Yeah.
So I don't know what Alok and Konstantin, like, what about you guys?
Yeah, I am also working on the feature set myself. So, and basically what I am doing is, since as I said that my model is generic and it's not just targeted as LLVM, and we are also targeting different GPUs. So I have divided my feature set into several parts. We have some feature set which is related just to the hardware aspect of it, like what is the speed of the CPU, what is the speed of your core of the GPU, and what is the bandwidth between CPU and GPU, what are the different memories available. Then there are feature set which is based upon what is the parallelism that is available, that is what are the different threads that are available. And then again, there's a third kind of feature set, which is what are the different computations that happen. And for each computation, what we are doing is we are extracting feature for each and every different kind of computation, like if it is a multiplication operation or if it is a addition operation, and whether it is a multiplication for floating point object or is it an integer type, or if total, if I say, I really did not count how many features I have, but it's still in 2 digits, but it's close to 70 or 80, something like that.
Okay, cool.
Ondrej, I think you're doing our embedding all together, right?
Yeah. I think feature or defining features is too hard for me, so I'm just using embeddings and train an embedding vector for each element of the language I'm operating on, and that works too if you can do it.
Right, but that is not like your code is still not like open sourced right now, right? People cannot actually use that.
Not yet, but people could look at ITEML or the ITEML paper by Jared Mendis, and they're doing the same thing for embeddings.
Okay.
Sorry, are there any plans of making it public, or it will not be? So.
There are. It's conditioned on finding a user. Basically, open sourcing and maintaining it in the open is takes an effort. So I'm planning to do it if there are people who would be using it.
Okay.
And for obvious disclosure, we are working with Ondrej on that because we are very excited about having that for performance problems, right? So it's just that there's only so many of us, and things take time.
Yep.
And we are all within Google, so it's not there need to be like a customer from outside.
Okay. So let's move on to our next question. What hurdles have you encountered working on ML and LLVM, and what solutions have proven valuable? I'm not sure what's so funny about that.
Oh, just because I just ran through so one problem, how to put this, one problem is that the code, that's my experience at least, doing in working the project that Yundi and I are doing, so the code isn't necessarily, there's lots of pitfalls, pits of failure that you can jump in, and because what we are doing is large scale, with a large amount of data, things might not necessarily be testable in a unit test sense. You might think that you are oh, it's fine. The unit test is, I'm doing the right thing, I'm extracting the right features. And then you discover that, well, when you actually do it at large scale and you extract profiles, and well, actually it's a bug. So there's been a lot of we do something and then Yundi looks at the data and she's like, well, this looks weird. And actually, Tarindu, you hit a similar thing, right? Where you did, it seemed right, but when you extracted the features, they were oh, wacko. And there's a lot of this data debugging that is very foreign to me, at least as a compiler engineer. It's not that's what I signed up to do. That's why I was laughing. It's just a bit weird to.
Right.
Tarindu, can you tell your?
Yeah. So, sometimes the models and everything seem to work, but they are not actually working. It's it happens some dumb luck. So the model might be not accurate, but it might give you accurate results even if it's not accurate. So it happens you have to be very, very careful about those things because if you're not careful, you are training a wrong model, but because it gives you some right results, you could be thinking you are having accurate results. So it's something you have to be careful for.
So it seems like data debugging, basically this is a large scale data debugging that is, so maybe there's some way to either offer some tools or that we can look at, because right now we've been doing it manually, right? I do something, then we look at the data, then Yundi is pointing out that this looks really strange, then look some more, then we realize why. So maybe something that can help a developer visualize that and see, because a lot of it is stuff there's lots of zeros, for example, and when you look at it, okay, it's kind of shouldn't really be like that. Or Tarindu, you hit something with 90-something% of the features were the same, right? So then you're well.
They had a small bug somewhere in the extraction. So
But there's the other thing, you don't realize it's a bug until because if you do a unit test, fine, it came out right, but so you need actually the big data scale, and it's kind of weird because so I don't feel that we yet have a full answer on how this is going to work, but probably it's about this data debugging and some data visualization. So Alok,
Alok, you go ahead.
Oh, yeah. I don't know the exact answer to this question as well. As soon as I find out which solution works, I'll let you know. Just like at Tarindu, as I said, we have been trying with different models and different solutions, and whichever works. Some solutions work in some scenarios, some doesn't. So I don't have one single answer. We have tried with multiple models. Finally, I saw neural network kind of works for me. And right now, the model that we are training is using deep residual regression model. And well, but again, it's not carved in stone. We are going on experimenting. We are just checking.
So validating your data that you extract out of programs is probably kind of the takeaway of this, because, well, if you feed in whatever into a model, it will spit out something. So that's great. Okay, we can move on. We have another, we had a question about the features already. Let's move on to the next one. People should feel free to still ask some more questions. We have a few more minutes left. How does one get involved in any of these efforts? Is there kind of a list of things that are going on, or ways to kind of collaborate with people that are already started, and so on and so forth? How did you guys maybe start this, or how could we kind of people reach out to you and get together?
We have a monthly, right? So we have a monthly meeting, and we didn't have it this month because we are doing this, right? So and I send every month so it's on the first Friday of each month, and I send a few days before the link. So long story short is so if you can't wait until December or January, ping us, and we can give you but it's a meeting invite. There's a shared document. People can put agendas there, and it's all within the LLVM dev community. So the only reason for joining the group is to get the meeting invite in your calendar for free, kind of a thing. It's just automation, but otherwise it's the LLVM dev community. So we're part of LLVM, right? So there's nothing more special than that.
Okay, sounds good.
That's very special, yeah.
No, it's great. I mean, it's good. It's good to know that there's this monthly meeting, and people can use that to get in touch. I mean, that is probably one of the easiest ways.
I mean, that's a very quick way. I would say, if you're interested in this thing in particular, come to the meetings, attend, and then talk to us, whoever in this panel. It's the same people in the meetings too. So and LLVM dev, it's all the same. Yeah, we're just LLVM developers.
Okay, great. So we have another question here that is, are there any considerations for a multitask IR embedding that would be used by multiple machine learning passes? So it's similar to the feature extraction, having kind of a generic feature extraction pass that multiple people use, and that just has you basically just extract a subset of those features for your particular use case. This might be could we do kind of a generic embedding and then use that at different places? Is there anything right now? Is there plans? What do you guys think about it? Ondrej, maybe this is one for you.
Well, I've been doing multitask learning on my performance models, but multitask means I'm just training all the different microarchitectures at the same time. Okay. And that helps. But I'm not sure this would be really easy to generalize to other tasks, simply because what I'm looking at is machine code or MC-inst in LLVM terms. And if someone is working on IR, I'm not sure how to connect the parts.
Okay.
I'm also skeptical. So my opinion is that we should have a number of, a number bigger than one, right? And so a couple of things that over time we work on and start seeing what the commonalities, if any, are, right? So I'm skeptical right now by having looked at two things, so inlining and register allocation, because there's nothing common. Like, I mean, live ranges are a totally different beast. Like, but maybe there will be things common, like when we start doing our embedding and other stuff like this in a future or something like that. So, and maybe when you keep chomping it, like, you realize that maybe there's some. What I'm trying to say is that we should. I think this is the thing, that the more parallel efforts there are, the more the discussion, the commonality will just emerge, right? Like we realize, oh, this is common, so let's not look at it. Let's just factor it, right? Whatever that is, like methodology or topologies of networks or code or whatever. So, yeah, we'd like to have that.
Okay, let's go on, move on to the next question. So what are some opportunities to do transfer learning from a deep learn base cost model? Would it be possible to use it to train models that judge whether a speculative transformation should be made? So as far as I understand, that we kind of provide a base cost model already, and then from there we kind of just go, to cost model for transformation A and B and C, and try to kind of specialize it such that we have. Is that something that you think is interesting? What do you guys think?
Yundi,
Yundi, the ML expert.
So I'm not sure what the transfer learning is going to transfer transfer from what objective to what objective. So I would imagine that would it be a possibility that we have a cost model trained on some architecture, then could it help in terms of having a cost model on a different architecture? This may be transferable depending on how different these two architectures are. There may be a possibility for that. So, Ondrej, what do you think about it?
Yeah, I have some hopes in that area. Sadly, I don't have any results in that area. But transfer learning from one microarchitecture to another is something I'd like to see working, because it would save us time training. But at the same time, whenever a new architecture or microarchitecture is introduced, very often it brings new instructions, and it's hard to transfer from it's hard to transfer to instructions which didn't exist previously. So we don't have any base data. I see what could be interesting is some kind of semi-supervised learning, or some combination of analytical models and learn models. Sorry.
I'm a bit hesitant in answering this question because I'm using a model which tries to predict on multiple different architectures. And one of the ways that we are looking at it is, okay, we can build for some architecture right now, and in future we build upon those models and using transfer learning. But my knowledge of transfer learning is it's not too much. I have not yet fiddled with that idea. So right now I'm training everything together.
Unfortunately, we are out of time. So I thank our panelists again, and everyone that was on the screens watching, all the people that asked questions and voted the questions. And as maybe kind of as a conclusion, feel free to join the monthly meeting that Mircea mentioned. Reach out to the panelists, reach out to me if you have any questions, and then we'll get you involved. This is very much kind of a very an actively growing field that is at the beginning. So we're kind of figuring things out as we go. We got our resources this year, we get our meeting this year, and so on. So please feel free to kind of join this effort. Okay, then thanks again to the panelists, and thanks for all the people. Hope you have a great rest of your day.
Thank you.
Bye.